So, Sebastián was one of the people animating the workshops on the first day, on Tuesday, with Veronica. Did you appreciate his workshop? No, you're not allowed to say that. Don't forget, you can always put comments on, including the workshops for those who attended, and on all the talks on SCAD, so we can provide feedback to the speakers. So be nice, but it's important. Okay, so this presentation on behavioral relationships of malware connections by Sebastián from Prague and from, Czech Technical University. And originally you come from Argentina. Yeah, and it's important for him. So you have the floor. Thank you.
Thank you very much. So hi everyone. Hi up there, the people. There is people there. Then they're awake actually. Most of them. Hi. Well, my name is Sebastián Garcia. I'm coming from Prague. I'm researching in the Czech Technical University on machine learning and network security on malware. And the talk is called Detecting the Behavioral Relationships of Malware Connections. Before we start, I would like to tell you that if you access this link in here, bit.ly/BotConf, you will see the slides live moving while I'm moving. So you can click on the links and copy paste or whatever. Maybe it's easier if some you people cannot see it. Yeah, so just get in there and you will see closer. So why I'm here, this is a 30-minute talk and it's gonna be pretty fast. And the thing is network detection, malware, botnet, yeah, we are there, we want to detect stuff. How we are detecting it? So far, the best we have is IOCs, right? Reputation, people there, putting this domain, this IP, virus total, passive analysis, a lot of people analyzing. And this is the best we have. And this is working, right? Snort, Suricata, Bro, maybe Bro now because there is a language in there. But IOCs are the best we have in the network, right? The problem is that IOCs are not enough. I'm not sure your experience, but in my experience, they are not enough. Especially when you have new stuff, new botnets, new malware, malware adapting, changing behavior. This is not working. You saw it. You go to virus total, you put something in there, and if it's too fresh in the first 3-4 days, no one is detecting that. This is very common, happen every day, nothing new. So what can we do, right? Like, what can we use if we cannot do that? And in the network, especially the payloads, the data, the pickups are not always available. So you cannot have the content, so you cannot apply your signatures or whatever. Okay, maybe sometimes you have the flows, right? Net flows, all this stuff, but what can we do with this? And this is where we start researching, okay? And we are saying, hey, you should go to behavior. Fortunately, there were some talks today talking about behavior. That's the way you should go. Yeah, IOCs are great. We are not going to stop using them, but we need something more. And the behavior here, it's looking at the intention, looking in time to what the malware is doing, what the botnet is doing. And this is going to give you more things. The problem is like behavior is nothing like packets or something like that. So what can you do with behaviors? Like, yeah, and like, should I use like machine learning or something? It's like, oh my God. And okay, what's the thing with machine learning here? So who in the room is using machine learning like every day or something? There's somebody here. Not. Come on, you never access Amazon, for example? Twitter is using machine learning. Facebook, machine learning all the time. What you see, what you don't see, what they are recommending, what they are showing, your feed, that's machine learning, guys. Okay, so in network security, this is not working so well, right? And this is the thing, like, is it working, machine learning? So the general feeling is like, nah, not working, right? Kind of a buzz. Or once I hear that, these companies that a lot of doing machine learning, I hear that machine learning is like teenager sex, right? Everyone says they are doing it, but nobody knows what they're talking about, right? And it's exactly like that. Like, come on, machine learning is very good, but it's not working. Nobody cares, but you should be doing it, right? If you're not doing machine learning, you are out, but it's not working. So the thing is, even if you don't like it, at some point you will have so much data and such a few amount of time that you need to start automating this. You start doing scripts, running tools, looking at the data. You don't have the people, you don't have the resources. So that is the path to machine learning. Maybe dark path, but it's a path. At some point, you start automating. You need to automate. And that's where machine learning can help you, okay? The problem is that, yeah, with machine learning, you have validation, you have results. You can check what you're doing, but nobody's checking the humans, right? Did you ever go to a human and say, okay, you, today, your false positive rate was 2%, you're fired. This is not working, right? Nobody's checking. And humans, we make mistakes. The problem with machine learning is that we can check exactly how good they are. Which are the errors, where are the errors? If this is not working, we blame it, and it's correct, right? Sometimes this is not working. So, in the university, we are doing the Stratosphere IPS project. This is a free software machine learning behavioral intrusion detection system for all of you to go download and use. We are using flows, we are using behavioral techniques, and we are doing this especially for protecting NGOs. So following the path of the Citizen Lab, we want to help non-governmental organizations because they are at risk. Nobody's helping them. They're being attacked every day, a lot, powerful actors, and they don't have the resources, they don't have the money. So from the university, we are trying to offer this tool, advanced machine learning, for free to NGOs. You can go there, you can click and see the information, data set. We have a lot of PCAT for you. Everything is free. And how we are doing this? Very, very fast. I will tell you that we start looking at flows. And from these flows, we create a connection of all the flows when you're accessing a certain service. So we see you, how you are, for example, checking Gmail or tweeting or whatever, and we can analyze extracting features, 3 features for each flow, and we assign a letter to each flow. So in time, we can have these letters saying A, B, A, B, X, and this is modeling your behavior in time for this connection. Based on this, we later learn some Markov model chain, and then we use the Markov model in the network to find unknown stuff. So we have the known malware behaviors, we store that, we learn, and then we go to a known network, say, give me the flows, okay, give me the letters, okay, is these letters belonging to this malware behavior? No. What about this one? No. What about this one? Actually, yeah. And we are detecting like this, okay? I'm telling you this, not because this is what I want to talk about, but this is not working all the time. And this is why I'm here. Of course, we have errors. This is machine learning. And starting to analyze these errors, we realize that some connections, normal connections, look exactly the same like some botnet connections. This is not new from the point of view of the network, but from the point of view of the behavior, this is very, very difficult. So we couldn't separate them correctly. And then we went to a new research path. So we are proposing something new here. It's like, hey, maybe we are looking too closely at the data. This is the letters from the Upatre botnet. And you can see that even if you don't look at the letters, it doesn't matter. You can see that there is the same behavior in each connection. It's very similar. This means that there are a lot of connections to different IPs and ports that they are doing something, but especially they are all doing the same type of behavior. So we say, hey, instead of looking at one connection, why don't we go up and we try to find the relationships between these connections in the network? So this leads us to graph analysis. So we say, okay, what about this, right? We know that the malware is generating this connection because it's software. There is an algorithm here, right? So we hypothesize that the relationships between these connections can be modeled properly. This is our first idea. So say, okay, how we can do this? Let's create a graph, I will show you now, for each source IP address, okay? And then each node in the graph, it's not the IP address. Usually when you see a graph, each point is an IP address. Here it's not like that. Each point is a destination IP, a destination port, and a protocol, okay? So each time that you see a point in the graph, it's actually a specific connection to some specific port. And then the sequence of flows from one node to the other node, those are the edges, okay? I will show you now. So what's happening here that thanks to our student Daniel Schmolik from the Stratosphere team that he created these graphs, every time that an edge between two nodes is found, the edge, the line is thicker, okay? And every time that a node is repeated, that means that the computer is connecting again and again and again, then the node is bigger, okay? And the more times a node is looping with itself, because it's repeating, then the colors gets darker. So this is an example of a normal behavior. Normal user, any day, going in the network, you see here some big nodes, a lot of edges in here happening, okay? I will show you another normal computer, a little bit more complex, more nodes in here, more loops, more edges. Some edges are repeating more than others, okay? And now I can show you an example of a ransomware, the server ransomware, and you can see that there is some difference, right? And this is the key. From this to this, you don't know what, but this is not the same. Actually, from there, I'm sure you cannot see it unless you are seeing the live slides, but there are lines in here, and this looks like a path. This looks like a very big loop that it's unfolding. Sometimes it reminds me of DNA, like it's opening in there. So this time of big loops and big sequence connections that are all going around, it's typical from the server ransomware. Actually, it's one of the only ransomware that it's generating so many connections, right? This is not typical. So we have the graph, we have the data. Humans can look at it and say, oh, okay, maybe I can separate this by looking at it, but we want some analytic things. We need numbers in here. So what we are saying is, let's count these. In each graph, let's count the number of nodes, the number of edges, the number of times a node is looping with itself, the number of times an edge is repeated, and especially the percentage of repeating edges from the total amount of edges. I want to know this host, how many times is repeating these connections from the total. So now we can compute something. And look at this. The server ransomware, 566 nodes, 600 edges, auto-looping nodes 20, and repeating edges is 590. That gives me 84% of the edges are repeating. And in the normal case, only 2.2%. And in the second normal case I show you, 0.21%. So we start looking at some trend in here that malware connections, botnet connections, not all of them, but most, are having this specific behavior in the network because they need to connect, because they usually connect to the same IPs of the domain, because they are doing this for a long time. So this percentage is going up. And in a normal computer, any guy or woman that is typing in there, you are accessing a web page, I don't know, for an hour, 2 hours, not Twitter, right? But normally you are like minutes in a web page or using some service. Email specifically is different, DNS difference, of course. But this trend, we saw that we can use this for detection. So this is the extreme normality case. Believe it or not, this is normal. The user is doing a lot of stuff all the time, a lot of plugins in the browser, and this is completely normal. However, when we analyze this with our technique, we see that we still have 0.99% of these repeating edges. So even though there is a lot of data, we still see the trend being respected in this normal connection. So of course, 3 examples is not enough. We make a lot of tests and other normal connections, 1.1, 1%, 0.9, 0.9. And then we test a lot of other malware. You can see here the varies 100%. A special infection that we did, that we have a normal user using the computer for several days. Then we infect it with the ransomware, and we can detect this because it's 99.75%. Low-key ransomware, 97.95. These are the links to our datasets in the Stratosphere webpage. These are 3 datasets that you can go and download the pickups, the binaries, and everything from there. So this is an ongoing research, but we found that looking at these specific behaviors, we may be able to analyze and detect malware from a new perspective. Specifically, this one is Sality, still alive, very big, a lot of people researching on this. This is only one computer for something like 5 hours. You can see that it's a mess, okay? And incredibly, Sality is changing so much its IP addresses peer-to-peer that the percentage is 6.2, right? So it's in the limit. Maybe we can say this is normal. Maybe we can say that this is malware. Machine learning therefore tell us at the end. So this is all I want to tell you. I want to share you very, very fast our last research on here. The idea is, I want to take you, hey, behavior, go there. IOCs, keep using it. It's going to save you. But in the long term, you have too much data. You need to start analyzing behavior. What's going on in time, making relationships, saying, hey, this looks infected. But actually, when I'm looking at all the traffic, this doesn't make sense. So this is not malicious, okay? And these behavioral relationships seems to be consistent. We are still doing analysis. We are executing a lot of malware every day, trying to merge this up, trying to come up with new ideas. But we think that we will be able to incorporate this inside Stratosphere very soon and offer it for free also. So that's it. Thank you very much for staying. My data here, the data sets of the pickup for you to go and download in there. Thank you very much for staying.
One, two. Yeah, we have time for a few questions. 1 or 2 questions. Come on. Upstairs.
No. You can jump, Wayne.
Yeah, jump. A question downstairs? What's your next step? What do you want to do next?
Well, right now we are merging this graph with neural networks and some anomaly detections, because the best thing is not to use only one algorithm, but to have like layers, right? So this is able to detect what Stratosphere originally cannot detect. So we are going to use both in line, right? So this is the way to go now, right? Having some filters in there, and this algorithm is saying yes, but the other one is saying no. So you are balancing in there, right? This is.
Okay. Wait.
Hi, Wayne Crowder. I'd like to know two things. The false positive rate, have you found any collisions or problems with like content delivery or other types of networks that could have mass connections? And then are you doing anything with Stratosphere to detect things like click fraud or stuff that would be use a similar type of research?
So about false positives, yes, we have. Actually, the problem with the false positive is that to actually count a false positive, you should know if it was normal, right? And how do you know? Because I use my tool? That's not the way to go, right? So at some point, you need humans checking and saying, yeah, this is working, this is not painful. Our last result is that we have something like 0.00007% of false positive rate, which sounds amazing. It's crap. It's horrible, right? This is giving us something like 20 false positives per half an hour in a very big network. It's horrible. This is the thing with machine learning. Imagine every time we are giving a false positive, some network administrator is running and I don't know, taking down some computer, right? So we need to keep working on this. That's why this new research, right? To keep it taken down. Also about the false positive rate, since this is free software and we don't want to sell it, we don't care saying when this is not working. And this is usually very hard to find in other environments. And about adware, yes, we try, it's very difficult. Some adware, it's, okay, yeah, here there is something, and other adware, it's just like a ghost, like few connections, actually looks like advertisement, and it should not detect advertisement. So it depends on the click frauding, if it's an extension, something we get, something we don't, yeah.
Okay. Blue.
Yeah, have you looked at what it looks like when you remove the destination port from the feature set? Does it do you observe the same behavior, or does it look completely different?
Well, in the case of Stratosphere, we are grouping all the flows. It was about the destination port, right? If I'm correct. Okay, so actually it is. We get all the flows, but we group the flows based on destination IP, destination port, and protocol. So every time that you're connecting to some IP and you change the port, for me, it's a new connection, right? And this is very important because, of course, the same IP can deliver several services, and each port in each protocol is doing completely something different. So we should focus every time you connect to the same IP, same port, same protocol, we group them all together. So yes, it's not a feature, but it's part of the grouping of the connections, yeah.
Yeah, hi. I was wondering about low-frequency malware. Would you be able to detect it, like, for example, one connection a day? Because a user usually connects multiple times to Facebook, Twitter, or whatever.
Yeah. With this technique, I say that we are grouping flows. I don't care. You can send a flow every once a year. We will get it, right? So we are using periodicity for this, but we don't have, we are not using frequency like Fourier transformation or nothing. So we are getting your periodicity, and if you match a model, I don't care. You can send every once a week a flow. If I have enough flows, 3-4 flows, I will get you. So it's not about if your periodicity is low or high. It's about if your periodicity, with the other features, it's similar to the models we know about malware, right? So if we have some malware with these features and you're similar, we detect you. If you're just periodic, like Twitter, hey, no, it's okay.
More questions?
Up there?
One? Okay, thank you very much.